Good morning. Uh, Today we will discuss about feedback control scheme and feed forward control scheme. This is the class for process dynamics and control, and in our last two classes we have discussed about the fundamentals of process control, control actions, and the major important part of control loop is process plant. So various characteristics of process plant is very much important in order to designing a control loop. And there are number of process control variables related to process plant. Those are self-regulation, potential values, and process time lag, process resistance, process capacitance, and we have modeled few systems, a few processes in terms of process time lag and process resistance capacitance, that is like in terms of electrical analogy. Now in our last class also we have mentioned that most of the closed loop control systems are feedback control system. What is feedback control system? Control system by which the control variable is measured, and accordingly if the control variable deviates from the set value, then only the corrective action is taken by the controller. Like this is the process, and process this is the outlet. So the process variable which is to be maintained at the desired value is to be measured, and that measured value is compared by the controller with the desired value, set value, and the deviation signal, that actually the driving force to the controller, then the controller will generate the corrective action accordingly. Then the energy adjustment to the process, this is the manipulated variable, that means the energy flow should be adjusted accordingly to the process, so that the process value, that is the control variable, can be maintained at the desired value or set value. So this is the feedback process, that is the process value is measured by the measuring system and the signal is feedback and compared with the desired value, and accordingly the corrective action is taken. So this is the control variable measurement process. So the important thing is, for feedback control system, the measuring system is the control variable. This is very much important term, that control variable measurement and control variable, accordingly the corrective action should be taken. But the point is, why the process value deviates from the steady state value. Suppose the process is running at a steady state condition, that means the measured value is maintained at the set value. That is why the process is stable and maintaining the steady state. But due to certain disturbances, those may be various disturbances, and those disturbances are in terms of process variable are load variables. So load variables are the variables. So load variables are the variables. Load variables are the variables which are the cause for disturbance, cause for deviation. That means when the control variable deviates from the measured value, that is due to various load variables. And just recalling the example of heat exchanger, if this is a heat exchanger system as per our earlier examples also. So for heat exchanger, that load variables may be the feed flow rate, that is the cold water flowing flow rate, and maybe the cold water temperature, that is cooling media temperature, cooling media flow rate. These may be the ambient temperature. Those all are load variables. So load variables, due to deviation of these load variables, the control variable deviates from the set value. So just think about the point that if we can measure those load variables, those are the cause of occurring deviation in a process, and if we control the load variables, then the deviation will not be reflected at the outlet, isn't it? So if we can measure the load variables and can control the load variables, that means if any deviation or any changes occurs in the load variables, accordingly the corrective action should be taken in such a way that the effect will not be transferred at the outlet. Though this is the ideal situation, but still this is the concept of feed forward control system. For feed forward control system, okay, and before explaining drawbacks, that feed forward control system is that the load variables should be measured, and accordingly if the control action can be taken, then the outlet, see, this is the outlet of this process, and this is there is no controller and other control scheme arrangement, that is, this is the controlled output. This is controlled output, no additional controller and measuring system, rather the control loop is not added at the outlet. This is the feed forward control system. Now feedback control system, mostly the control loops are feedback control because of the easiness of its operation and application. Very simple, just the process output is measured, and if deviation occurs, then then only the corrective action will be taken, and a deviation signal is the controlling signal for the controller, and accordingly the controller will generate the corrective action so that the manipulated variable or manipulated energy flow to the process will be adjusted accordingly. Now what are the drawbacks of this process? Drawbacks, I also mentioned in last class also, that the drawback of feedback control system is error is inevitable in the process. That is unavoidable. Unless error occurs in a process, no corrective action can be taken. So error is unavoidable in the process. So for those systems where certain tolerance is acceptable, for those type of process control system, feedback is applicable, where a tolerance, that means the output variable, which is the control variable of the process, that should have a certain tolerance. Suppose for this heat exchanger, the outlet temperature desired value is 70 degrees centigrade. So this should be, outlet should be maintained at say 70 degrees centigrade. Now this 70 degree is not, cannot be maintained for all time. There must have a tolerance. That means for the controller, the output should have some plus minus say 5% or 2% tolerance. For this kind of system, feedback control system is alright, but for where this tolerance, for delicate system, where very much accurate system is required, only 70 degree or 71 degree is permissible. for those kind of system, feedback is not the suitable method for controlling of a process plant. So the drawbacks are, the feedback control system is not capable of correcting a deviation produced in the control unit from its desired value just at the time of detection. This is the problem of delay, that when it is detected and where it is corrected, there is a certain time delay due to the loop. The deviation occurs within the process due to the presence of disturbance, and there are several steps before energy adjustment to the process. So there are several time delays. In last class, I also discussed about the closed loop control system time delays. So there are several time delays for feedback control system. These delays are again unavoidable. In many processes, there exists a finite delay between the manipulated variable and its effect on the control variables. For a larger delay, the process may be submitted to frequent disturbances during delay time, and hence it is difficult to restore perfect balance by feedback control system. That means when the error occurs and when it is corrected, there is a certain time delay. That's why I have mentioned that for those systems where a certain tolerance is permissible, then only the feedback control system is applicable. Next is, deviation in a control system, a control variation must appear before any corrective action can start. That I mentioned just now, that error is inevitable in a process. Error cannot be avoided. The value of manipulated variable needed to balance the load must be obtained by trial and error method. That is another problem, that the manipulated variable, that is the energy adjustment to the process, should be adjusted by trial and error method. That means the difference is calculated, and accordingly the manipulated variable is valve opens due to control action, and manipulated variable is adjusted, because we do not measure the disturbance values. We are not measuring the disturbances, that is the load variables. So the manipulated variable, that is the energy adjustment to the process, is purely by trial and error. So this is another problem in feedback control system. And load variables can be divided into various components. Like load variables are many, just like heat exchanger problem, maybe due to feed flow rate, feed temperature, feed ambient temperature, or feed composition, whatever be. So load variables are many. Hence there must be always at least one manipulated variable for each independent control variable. So but for feedback control system, the manipulated variable is a single variable. That means the energy adjustment. That is one part. But the reason is multiple. We are not eliminating the reason, rather we are just trying to achieve the set value for the output. I think I am clear about feedback control systems and its drawbacks. Now for feed forward control system, this is load variable measurement system, where the load variables should be measured, and there should be a mathematical model by which the energy adjustment should be in such a way that the error will not be reflected to the output. Again, this is the ideal situation. Now, when the disturbance is measurable, feed forward control is an effective means for cancelling the effects of disturbance on the system output. This is another point, that always all the disturbances are not measurable parameter. So when the disturbance is measurable, then only feed forward control system is effective. This is advantageous. Of course, this is advantageous because for feedback control system, corrective action starts after the error reflected at the output. But for feed forward control system, the change in disturbance signal is measured and corrective action takes place immediately. So the delay for the control loop is minimum and the error is not reflected at the output. As a result, the speed and performance of overall system improves. So, but for real system, real feed forward control system, always the feed forward control is used along with feedback control system. The real feed forward control system is always used along with feedback action. This is because that if since for feed forward control system we need to develop a mathematical model so that the energy adjustment should be such that error should be corrected before reflecting to the outlet. Now this is again mathematical model, so there must be certain error. So if any deviation is reflected at the outlet, then feedback action will take care of that error elimination. Now this is the scheme for feed forward control system, again with the example of heat exchanger. See, this is the heat exchanger, and for heat exchanger there must be inflow. This is the cold water flow path, and the outlet is the hot water or controlled water that should be maintained, and this is the jacketed pipe through which the energy flow, that is the steam or whatever be the heating media, should be sent. See, this is the steam flow path. Through this the steam is flown, and this is the outlet of this heat exchanger, right? So this is the inflow path, and this is the cooling media fluid flow path, this is heating media fluid flow path, and this is the heat exchanger output, that is the process variable, which is to be maintained at the desired value. Now see, as we have mentioned that the load variables are maybe the feed flow rate, feed flow temperature, feed water temperature. So feed water temperature is measured by each individual load variable should be taken care for measurement and control. The flow rate is measured by flow transmitter. Temperature of feed flow, feed water should be measured by temperature transmitter, and all these variables are input to the computer, where that is the mathematical model for feed forward control set value generation. This is the actual set point at which the outlet should be maintained, just like the previous example, say 70 degrees centigrade. So this should be maintained at 70 degree. So comparing all these, the feed forward set value is set to the controller. This is the actual controller, and the controller set value is generated by comparing the real set value or actual set value with the load variables, comparing the set value with the load variables. So if any deviation occurs in any of the load parameters, then the feed forward set value will change accordingly, and the controller output Another parameter is the steam, that is the manipulated variable, just like the feedback control system. That is the steam. Steam temperature is measured, and that is input to the controller. So the controller, as I have mentioned, that controller is always a three-term device. So controller will compare the energy temperature of steam flow input with the feed forward set value, and accordingly the feed forward control action will be generated. So that will allow to flow the energy to the system. That means it will open the valve, open or close the valve accordingly, and it will adjust the flow rate, steam flow rate, so that the outlet temperature can be maintained at the desired value. So if any deviation occurs in any of the load variable, that should be corrected by feed forward set value, and accordingly the controller will generate the energy input or change the manipulated variable to the process. So it should be maintained at the desired value for all time. But even since this is purely the mathematical model, based on this mathematical model, the feed forward set value is generated. So if there exists any error, or due to any error, some error is reflected at the output, then that should be taken care by the feedback control system. This is purely feed forward, but for real system, feed forward is always connected with the feedback control system. In block diagram, this is the heat exchanger, the process value, that is the temperature which is to be maintained at desired value. Then this is the feedback part, and this is the disturbance. This is feed forward part. So measurement of flow and temperature controller, set value, and this will set the adjust the energy input to the process, and the outlet temperature should be maintained at the desired value. But even that, if deviates from the desired value to some extent, then that will be taken care of by the feedback control system. This is the temperature measurement system, and again this signal is sent to the controller. So the block diagram for that, this is the process GS, and the manipulated variable to the output is GS, and this is the GC is the feedback controller transfer function, and this is feed forward controller GF. This is feed forward controller. So and this is disturbance. GN. Sorry, this is GNS. So this is the disturbance function, transfer function. So just the block diagram is like that. This is the feedback part, and this is feed forward part. For real system, the transfer function, the representation is like that. If we simplify the function, then from that block diagram, then the transfer function CS is GC, GS, ES. This is GC, GS, ES plus this, due to this, that is NS, GC, GNS, and simplifying this, we will find that the relationship of CS and NS is like that. Now this is the component due to the disturbance. So if we want to select that the feed forward transfer function such that the effect of disturbance at the output is 0, that is our ultimate objective, that effect of disturbance at the output should be 0, then we require the coefficient of NS is equals to 0. So putting this equals to 0, we will get GF, that is the feed forward transfer function, is equals to this much. So the feed forward block should be designed in with this value. So this is the system for feedback and feed forward control system. Now the next part is control action and controller. Control action, depending on modes of control action, the controllers are different types, and as you have already completed linear control system, you know that the modes of control systems, control actions are the primary one is on-off type controller, and that is two-stage control system, either on or off, and the continuous controllers are proportional, PI, proportional plus integral, proportional plus derivative, and PID controller, proportional, integral and derivative type. So all these are continuous type control systems, control actions, and on-off control action is the two-step control action. And this is depending on modes of control action and depending on type of energy used. That means the controller is operated by the pneumatic signal, that is pneumatic controller, by electric signal, that is electric controller, hydraulic type, electronic type. And nowadays mostly all controllers are electronic type controller, and electronic type controller again are of analog controller, microprocessor based controller, fuzzy logic based controller, programmable logic based controller PLC, direct digital controller DDC, and distributed control systems DCS. All these are electronic type controller, but mostly nowadays DCS based controller and PLC based controller, all these are electronic controller. Now starting from the modes of control actions, two-stage control, that is on-off control, and continuous control. Two-stage control or on-off control again are of two types, that is without differential gap and with differential gap. All real on-off type controllers are with differential gap. If it is without differential gap, then how it can be defined? Without differential gap means, that is during operation the controller should operate with respect to the set value. That means, say for temperature controller, the controller set value is again say 80 degrees centigrade. Then the as this is set value, then the controller should operate at 80 degrees centigrade. When it goes below 80 degrees centigrade, then it should turn on. Just think slowly that if the temperature goes below 80 degrees centigrade, then controller should turn on, so that again the heating should start. And if it goes above 80 degrees centigrade, just cross the 80 degrees centigrade, then it should turn off. That is the simple mechanism of on-off control system, that when it exceeds the set value, then one operation, and when it goes below the set value, then other operation. But it depends on the definition of error signal. Error signal or deviation signal is the difference between set point and measured value. Now if we consider the deviation signal as set point minus measured value, then the control action can be defined as, one thing I should mention, that control action always should be defined in terms of change in manipulated variable, because the change in manipulated variable is the controlling parameter for the process. So every control action should always be defined in terms of change in manipulated variable, that is small m. So m is maximum when error greater than 0 and m is minimum when e less than 0. Again, think slowly that if error is greater than 0, just think the set value is 80 degree. If error is greater than 0, that means when the error goes above the error is greater than 0 means when set value is greater than measured value. That means when measured value goes below set value. Actually, set value is the constant parameter. Error is greater than 0 means when measured value goes below set value. That means when measured value is less than 80 degree, then the controller should turn on. That means the energy flow should be maximum to the process. So m is equals to maximum. And when error is less than 0, this is minimum. Now how it depends on the definition of error signal? Error signal is just the difference between set value and measured value. Not necessarily this is set point minus measured value. It may be defined as measured value minus set point. Right? So if one define the deviation signal as measured value minus set value, then the definition of this control action will be just reverse. For that case, if error is mv minus sp, then m is minimum when e greater than 0, m is maximum when e less than 0. So the definition of error signal is very much important for defining the control action. And this is without differential gap, means the action will be taken, control action will be taken just when the measured value goes below or above the set value. But what is the problem with this kind of operation? That the switching will be a continuous process. Continuously on off will occur. When it goes below, just below 80 degree, then the controller will turn on and it will reach the 80 degree and try to cross 80 degree. Then again it will turn off. So switching will be fast and that will cause a mechanical loss, wear and tear effect. That's why a differential gap is, for real system, a differential gap is introduced. Differential gap is the, instead of using 80 degree centigrade, it should be treated as, say, 80 degree, it should be treated as 80 degree plus, say, 2, 3 or 5 degree centigrade, plus minus. That means that is the band. So instead of operating to the particular 80 value, it should operate, say, 82 at the upper limit and 78 at the lower limit, or if it is 3 degrees, say 80 minus 3 and 80 plus 3. So the controller will turn on, or the output is maximum when the value is, error value, when it the measured value goes below 78 degree and when measured value goes above 82 degree. Clear? So this is the reason of utilizing differential gap. I will explain the dynamic characteristics of this process, then you can understand the difference between this switching action. Okay, so this is the definition of a dependency of defining the error signal, and again it depends on valve type. I will explain this valve operation in detail in valve in the class of control valve. Just you should understand, this is the pneumatic type valve, this part is actuator, and this is the stem. So whenever the controller output comes to the actuator in terms of pneumatic signal, then it will create the pressure and the stem goes downward. See, this is the this is called the seat, sorry, this is called the plug, and this is called seat. That means where the plug should be placed, and the flow path of fluid through the valve is through this, this and this. See, the path is like this, through this and this. This is the fluid flow path. This way. This is the fluid flow path, and the plug which you can see here, that is in figure, this is just the closed fit at the seat position, that is the under closing position. If the stem moves upward direction, then the valve will open the path and the fluid can flow through the. Otherwise, this is the fully closed position of the valve. That means it will restrict the fluid flow through this. Now, if the valve is of pneumatic type, then the again the definition of on-off control action, rather the function of on-off control action will depend. That means the valve may be of two types for pneumatic valve, air failure to open type and air failure to close type. What are those types? Air failure to open type, air failure to open type, and air failure to close type. Maybe or in some book it is written as air to close type and air to open type, air failure to close type or air to open type, air failure to close type or air to open type. Sorry, air failure to close type or air to open type. That means when air failure to open type means when air fails to reach at the actuator, then it remains open. When air fails to reach at the stem, then what will happen? If there is no air signal at the actuator, then the stem will be at upward uplift position. That means valve remains open. So air failure to open type, and air failure to open type is the air to close type. That means when air reaches to the valve, then it is closed. That means this valve is the, as it is shown here, this is air to close type. When air reaches to the actuator, then the valve is in at closed position. I think I am clear that air to close type and air failure to open type, these two are same, and the reverse is air failure to close type or air to open. Air failure to close means when air fails to reach at the valve, then it is at closed position. For that, this plug, this is called plug, which fits at the seat area in order to close the valve, that position at the lower portion of the seat area. This is the position of the plug. See, if the plug is of that type, then what will happen? When air fails to reach at the actuator, then the stem is at uplift position. So this seat, this plug will fit to the seat area. That is the air failure to close type or air to open type. For this kind of plug, what will happen? If air reaches, then when air is at the actuator, then always the stem is at pressurized condition, so it will move downward. So this is the case where this is the air to open type. I think I can explain the type of valve and how it affects the on-off control action. For on-off control action, if the controller output is maximum or minimum, that means the air reaches to the valve, then if the plug is of this type, or rather the valve is of air failure to open type or air failure to close type, if it is air failure to open type, that will function in one way. If it is air failure to close type, it will operate just in reverse way. So the energy that will flow to the process, this is the energy flow path, and that energy will that is the maybe for heat exchanger, this is the steam flow path. So this energy will send to the process. So this is the ultimately the operating that is the manipulated variable for the process. So depending on type of control action, rather on-off control action, that is the maximum energy input or minimum energy input, the for two different types of valves, it will, the energy flow to the process will be just of reverse type. For one type, the energy flow is maximum. For other type, the energy flow is minimum. So control action, on-off control action is dependent on valve type also. Since the flow path, this is the ultimately the energy flow, the manipulated variable to the process. And the on-off control action with differential gap. With differential gap means when the error signal is measured value minus set value or the reverse. Now you are clear what is the dependency of defining this error signal. The controller output should be generated as minimum and maximum when the error is epsilon by 2 and minus epsilon by 2. This epsilon is the differential gap. Just from the dynamic characteristics, we can understand that without differential gap, this is the set value. This x-axis is time scale. This is the time scale, and this is temperature scale. So this response characteristics, that is the this is set value, and this is the maximum position of the controller and minimum position of the controller. So the controller will change from the minimum to maximum operating position, and accordingly the process value, this is the dynamic characteristics of the process value, that is the temperature, will change see, when this changes from minimum to maximum, that is the switching occurs, then the temperature, when temperature goes below the set value, then the controller should turn on, that is heater should turn on. And now see the interesting feature that at say for this position, the controller is at on position, that means heater is at on position, but still the temperature is going downward. Why? This is due to the process transfer time lag. This is the inherent characteristics. As we have discussed in our second class, that there are different time lags. Due to the process transfer time lag, even when the controller changes its position, the heater circuit is on, but still it continues to goes below, temperature is continuing to goes below the set value, and at certain point of time it will sense the energy change, then it will start to rise. This is the time delay tau 1, and from here it starts to rise, and at the point when it just crosses the set value, then what will happen? The controller will turn off. So this is the downward switching of controller. Now controller is at off position. Again, see at certain say at this position, the controller is at off state. That means heater is at off state, but still the temperature is rising. That is again due to time delay, transfer time delay. That means the controller is off, but temperature is still continuing to rise, and at certain point of time it will detect that controller is off, then it will start to fall. This is the process dynamic characteristics, and this will operate, and the controller switching will operate at the point of crossing of set value. When it goes below the set value, the controller will turn on. When it goes above the set value, it will turn off. And this is with the differential gap. For differential gap, instead of operating at set point, this is the set point part, instead of operating at set point, there is a differential delay. This is the upper set value, this we call as upper set value, and this is the lower set value. So instead of operating at set value like the without differential gap, it will operate, the controller will switch when it goes below the lower set value, and it will turn on when it goes above the set value, upper set value. So the time delay is more than this one. So the switching, in order to minimize the mechanical loss, the switching can be minimized. That means the time delay between the switching can be increased, right? So this is the reason of using this on-off controller with differential gap, and all real-time on-off controllers are with differential gap. Okay, so next is the continuous type controller. In our next class, we will discuss about the continuous control actions. So today up to this. Thank you for your attention.